What if we're not alone? Tonight, we're exploring something that challenges everything we thought we knew about visitors from deep space. You've probably heard about asteroids and comets passing through our solar system. But here's what most people don't realize. We might have detected something that shouldn't exist. 3 Atlas arrived from interstellar space with characteristics so anomalous it forces us to question whether everything we see in the cosmos is natural. By the end of this journey, you'll understand why astronomers are considering possibilities they never thought they'd take seriously. Before we dive in, if you enjoy these explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Unsettling is going to be extraordinary. You've probably heard about asteroids and comets passing through our solar system thousands of times. But here's what most people don't realize about what happened on July 1st, 2025. What seemed like just another routine discovery would eventually force us to question whether everything we see in the cosmos is actually natural. On that summer morning in Chile, the Atlas telescope system did exactly what it was designed to do. Like a tireless digital sentinel, it scanned the southern skies, capturing frame after frame of star fields, looking for anything that moved. This is how we find asteroids and comets that might pose a threat to Earth, automated systems that can spot a moving dot among millions of static points of light. Picture this process for a moment. Every night, telescopes around the world take thousands of images of the same patches of sky. Computer algorithms then compare these images, looking for objects that have shifted position between frames. It's like playing an incredibly sophisticated game of spot the difference with the entire cosmos as your playing field. Most of the time, these systems find exactly what they're supposed to find. Main belt asteroids, known comets on their predicted orbits, occasionally a near-Earth object that needs tracking. At first, there was nothing remarkable about the detection. The computer algorithms flagged a moving object, assigned it a preliminary designation, and added it to the queue for human verification. Think of it like a librarian sorting through thousands of new books. Each one gets catalogued according to established procedures based on its characteristics: size, brightness, movement pattern, spectral signature. But this is where things get interesting. The initial orbital calculations revealed something immediately exciting. This wasn't just another space rock from our asteroid belt. The trajectory was hyperbolic, which means it was moving too fast to be bound by the sun's gravity. This was an interstellar visitor, only the third one we'd ever detected after Oumuamua in 2017 and Borisov in 2019. Think about what that means. In the entire history of human astronomy, we'd only confirmed 2 objects that originated outside our solar system. Now we had a third. The rarity of this discovery cannot be overstated. It's like finding a message in a bottle that's been floating across an ocean for millions of years. And honestly, that made perfect sense. Comets from other star systems should exist. The math is actually quite elegant when you think about it. During the chaotic early years of any planetary system, giant planets migrate inward through the disk of gas and dust surrounding their young star. As these massive worlds move, they gravitationally scatter smaller objects in all directions, like billiard balls on a table that's slowly tilting. Some of that material falls into the star. Some settles into stable orbits. But a significant fraction gets ejected completely, sent wandering through the galaxy for billions of years. Our computer models predict that trillions of these interstellar objects should be drifting through space right now. Invisible refugees from stellar nurseries that have long since evolved into mature planetary systems. Most are too small or too distant for us to detect. But occasionally, one passes close enough to our sun to light up and become visible. It's like fireflies in a vast dark forest. You only see the ones that happen to fly near your campfire. The numbers are actually staggering when you calculate them properly, with roughly 100 billion stars in our galaxy. And most of them having gone through this planetary formation process at some point, the space between stars should be populated by an enormous diaspora of ejected material, rocks, ice balls, metallic chunks, all following their own independent orbits around the galactic center, occasionally encountering other star systems purely by chance. 2I Borisov had been the perfect example of what we expected from such encounters. When it approached the Sun in 2019, it developed a beautiful coma and tail, exactly like comets from our own solar system. Spectroscopic analysis showed all the right chemical signatures: water ice, carbon dioxide, methanol, hydrogen cyanide, sublimating as solar radiation heated the surface. The ratios of these materials matched what we see in comets from our Kuiper belt. It was a textbook case of a dirty snowball from another star system, confirming that the basic chemistry of comet formation is universal. So when Atlas appeared to be significantly larger than Borisov, that seemed perfectly reasonable. Interstellar comets should come in all sizes, from pebbles to mountains, depending on the violence of their original ejection and how they've survived their billion-year journey through space. Some would be fragments broken off from larger bodies during the ejection process. Others would be intact planetesimals that happen to get a clean gravitational kick into interstellar space. The chemistry should be predictable too. Comets everywhere are essentially the same thing: balls of ice mixed with dust and rock, frozen remnants from the formation of planetary systems, water, carbon dioxide, methane, ammonia, carbon monoxide. These are universal building blocks that condense in the cold outer regions of any star system where planets are forming. The laws of physics and chemistry don't change from star to star, so we expect the same processes to create the same types of objects everywhere. As Atlas continued its approach toward the Sun throughout the summer of 2025, astronomers around the world expected to see the familiar process unfold. Solar heating would start sublimating the surface ices, creating that characteristic fuzzy coma of gas and dust around the nucleus. This outgassing would make the comet progressively brighter and easier to study, giving us our best chance to analyze material that formed around another star billions of years ago. The physics of this process is well understood. As a comet approaches the Sun, solar radiation penetrates the surface, heating subsurface ices. When these ices reach their sublimation temperature, they turn directly from solid to gas, creating pressure that forces material up through cracks and pores in the surface. This creates jets of gas and dust that form the coma, and eventually the tail that always points away from the Sun due to solar wind pressure. The trajectory itself followed Newton's and Einstein's laws with mathematical precision. You could trace the exact path of this massive object as it fell toward the Sun along a curved space-time geodesic, accelerating under gravity's pull like a ball rolling down an increasingly steep hill. No mysteries there. Just physics doing exactly what physics does, with the elegance that comes from fundamental forces operating according to immutable laws. Even the direction it came from made perfect sense when astronomers traced its path backwards through space. The orbit suggested an origin in the thick disk of our galaxy, a region populated by older stellar systems that have had plenty of time to eject material during their chaotic formation periods. These are stars that formed when the galaxy was younger, when stellar densities were higher and gravitational interactions between stellar systems were more common. The timing of our discovery seemed natural too. Our automated survey telescopes had finally reached the sensitivity needed to detect regular interstellar visitors that had always been passing through unnoticed. The Atlas system, the Catalina Sky Survey, Linear, Neowise. These programs had been steadily improving for decades, and we were finally crossing the threshold where detecting interstellar objects would become routine rather than extraordinarily lucky. And with next-generation observatories like the Vera Rubin Observatory coming online in the next few years, astronomers expected to find dozens more objects like Atlas annually, finally confirming the vast populations of wandering interstellar material that our theories predicted. We were entering an era where studying visitors from other star systems would become a regular part of astronomy, not a once-in-a-decade sensation. This was like meteorites, but infinitely better. Instead of small fragments of asteroids that had been altered by their fiery passage through Earth's atmosphere, here was an entire intact comet from another star system, bringing us pristine samples of how planets form in different environments around different types of stars. We could study the original composition of materials that condensed in an alien stellar nursery, potentially revealing whether planetary formation follows the same patterns everywhere or shows interesting variations. We had the perfect instruments to study it too. The Hubble Space Telescope could provide detailed imaging of the coma structure and monitor changes in brightness. The James Webb Space Telescope could penetrate the dust with infrared observations, revealing the thermal properties of the nucleus and detailed spectroscopy of outgassing materials. Ground-based observatories like the Very Large Telescope and Keck could provide complementary observations across different wavelengths. The scientific consensus formed quickly among the global astronomy community. Atlas was clearly an interstellar comet, following well-understood patterns of sublimation and outgassing. Every major astronomical institution agreed. The discovery papers were drafted with confidence. Press releases were prepared, announcing this fascinating but perfectly comprehensible visitor from deep space. All the initial data fit the standard model beautifully. A natural object ejected from another planetary system billions of years ago, now making its first and only close approach to our sun before being flung back out into interstellar space forever. The observations matched theoretical predictions with the kind of satisfying precision that makes scientists feel confident about their understanding of the universe. During those first few weeks after discovery, Atlas seemed like a textbook case. Another wonderful example of how our understanding of planetary formation, stellar evolution, and interstellar space was fundamentally correct. The universe was behaving exactly as our best theories predicted it should behave. There appeared to be no mystery at all, just an unprecedented opportunity to study alien material up close for the first time in human history. Scientists around the world were excited, but not surprised. This was the natural next step in our exploration of the cosmos. We'd found our first interstellar asteroid with Oumuamua, confirmed our basic theories about interstellar comets with Borisov. And now we had an even larger specimen to examine in unprecedented detail with our most advanced instruments. The case seemed closed before it had barely opened. Atlas was filed away mentally as interesting but understood, just another fascinating chapter in our growing catalogue of interstellar visitors that proved the universe works the way we think it works. But then, the first detailed spectroscopic observations started coming back from the major observatories. And that's when everything began to unravel. The first crack in the consensus appeared when astronomers tried to calculate just how rare Atlas actually was. When you run the numbers properly, considering the size estimates coming in from multiple observatories, something deeply unsettling emerges, a comet this large, traveling through interstellar space for billions of years and happening to pass through our solar system should be extraordinarily uncommon. Think of it this way. Detecting an interstellar object over 5 kilometers in diameter within just 5 years of serious searching would be like casting a fishing line into a small pond and immediately hooking a whale shark. The statistical probability is so low, it makes you question whether your assumptions about the situation are correct. But the real problem started when the spectroscopy results began arriving from observatories around the world. For weeks, some of the most sophisticated instruments on Earth had been pointed at Atlas, breaking down its reflected sunlight into component wavelengths to identify what materials were present on its surface. This is how we normally identify the chemical composition of comets. Different molecules absorb and reflect specific wavelengths of light, creating fingerprints that are as distinctive as DNA. The results were baffling. It was like walking into a bakery, expecting to smell fresh bread and finding absolutely nothing. The characteristic spectral signatures of water ice, carbon monoxide, and methane that should dominate any comet's composition were either completely absent or so weak they were barely detectable. And there was something else that didn't make sense. Atlas was staying much brighter than it should have been for its distance from the Sun. Even accounting for the possibility of a diffuse coma of gas and dust around the nucleus, the object was shining like a flashlight with a battery that should have died long ago. When astronomers finally did detect gaseous activity around Atlas, the composition was completely backwards from what they expected. Instead of being dominated by water vapor like every other comet ever studied, Atlas showed a strange abundance pattern. 87% carbon dioxide and only 4% water. This was like finding a snowball made mostly of dry ice with just a sprinkle of regular ice mixed in. You have to understand how weird this is. In our solar system, comets form in the cold outer regions where water ice is the most abundant volatile material. The ratio of water to carbon dioxide is usually around 10 to 1 or even 100 to 1 in favor of water. Finding a comet with the reverse ratio is like discovering a beach made primarily of seashells with just a little sand mixed in. It violates our basic understanding of how these objects form, but the problems were just beginning to pile up. For Atlas to have survived billions of years traveling through interstellar space, it would need internal structural strength completely incompatible with the dirty snowball model of comets. Think about what this object has been through. Cosmic radiation constantly bombarding its surface. Occasional impacts from microscopic dust grains hitting at relative velocities of dozens of kilometers per second. Temperature fluctuations from near absolute zero to whatever heating it experienced when passing near other stars. A typical comet is a loose aggregate of ice and dust held together weakly by its own minimal gravity. Such an object should gradually erode and fragment during a billion-year journey through space. But Atlas showed no signs of this expected degradation. The polarization measurements were equally confusing. When light bounces off different materials, it becomes polarized in characteristic ways that tell us about the surface properties. Atlas was reflecting light with polarization patterns that didn't match any known models for scattering by ice, dust, or rock. It was like seeing a material that obeyed its own unique optical laws. Then, astronomers noticed something that sent chills down their spines. Atlas wasn't following a random trajectory through space. Its orbit was aligned with our solar system's ecliptic plane to within just 5 degrees. The probability of this happening by chance for an object on a random interstellar trajectory is less than 0.2%. It's like rolling dice and having them come up sixes 10 times in a row. When they calculated the precise orbital mechanics, things got even stranger. Atlas was going to pass remarkably close to Venus, Mars, and Jupiter with geometric precision that seemed far too convenient for an object supposedly following pure gravitational physics. It was like watching a billiard ball that somehow managed to bank off 3 exact spots on the table, despite being launched randomly. The entry velocity was wrong too, at 60 kilometers per second relative to the Sun. Atlas was moving at exactly the kind of speed you'd choose if you wanted to navigate efficiently through our solar system. Natural ejection from young planetary systems should produce a wide range of velocities, with most objects moving either much faster or much slower than this optimal speed. Even the direction Atlas came from didn't make sense. It approached from the southern celestial hemisphere, but theoretical models predict we should see more interstellar objects arriving from the north, in the direction our solar system is moving through the galaxy. It was like all the traffic on a highway suddenly started coming from the wrong direction. Perhaps most disturbing of all was the route Atlas had taken to reach us. Tracing its path backward through space, astronomers realized it had approached through the dense star fields of the galactic center region, an area where early detection would be nearly impossible due to the overwhelming background of bright stars. If you were trying to approach our solar system without being noticed until the last moment, this would be exactly the path you'd choose. The TESS Space Telescope revealed another impossibility. Atlas had been active since May 2025, when it was still 6.4 astronomical units from the Sun. At that distance, solar heating is so weak that normal comets remain completely inert, frozen solid like stones in deep space. For Atlas to be showing activity at such distances suggested either an internal heat source or surface materials that sublimate at impossibly low temperatures. High-precision astrometric measurements revealed that Atlas was rotating with a stable 15.5-hour period that suggested a solid, coherent body rather than a loose collection of debris. This kind of structural integrity was incompatible with the fragile nature expected from a comet that had wandered through space for billions of years, constantly buffeted by cosmic radiation and micro-impacts. The complete absence of fragmentation was perhaps the most telling anomaly. Every computer model of interstellar comet evolution predicts that these objects should show clear signs of erosion and breakup after such extended journeys. They should be surrounded by trails of debris, missing chunks, irregular shapes from impacts. But Atlas appeared pristinely intact, as if it had just left its home star system yesterday instead of billions of years ago. When detailed imaging finally revealed the structure of material being ejected from Atlas, astronomers discovered something that violated basic physics. There was a jet of material pointing toward the Sun, the opposite of what should happen. Normal comets develop pressure from sublimating ice that pushes material away from the Sun, creating tails that always point in the antisolar direction. Atlas was somehow doing the reverse, as if it were pulling material from space rather than ejecting it. Precision orbital tracking detected subtle deviations from the path predicted by gravity alone. Atlas was showing tiny non-gravitational accelerations, like a car that occasionally changes direction without the steering wheel being turned. These accelerations were far too small and controlled to be explained by random outgassing from a natural comet. Spectroscopic analysis of the surface materials revealed another chemical impossibility. The abundance of nickel exceeded that of iron, completely contradicting universal patterns of how elements condense in protoplanetary disks. In every known natural environment where rocky materials form, iron always dominates over nickel by a large margin. This reversal was like finding a type of wood where the bark was harder than the core. But perhaps the most spine-tingling discovery was made when astronomers traced Atlas's trajectory back to its point of origin. The direction aligned to within 9 degrees of the famous WOW signal detected by SETI researchers in 1977. For a randomly oriented interstellar trajectory, the probability of this alignment occurring by chance is only 0.6%. It was as if Atlas had been sent from the same region of sky that had produced the most compelling evidence for artificial signals in the history of radio astronomy. Computer simulations designed to model natural comet behavior were completely unable to reproduce the observed patterns of brightness, activity, and material ejection from Atlas. Every attempt to fit the data to known physical processes failed catastrophically. It was like trying to explain the behavior of a jet aircraft using the physics of bird flight. The fundamental assumptions were simply inadequate for the observed phenomena. And this is where things became truly unsettling. Each of these anomalies, taken individually, might be explainable as some kind of rare but natural phenomenon. But when multiple independent improbabilities occur in the same object, you have to multiply their chances together. The combined probability of all these anomalies happening simultaneously in a natural object approaches zero so closely that it becomes essentially impossible. It's like flipping a coin and having it land on heads 20 times in a row. Technically possible, but so unlikely that any reasonable person would start suspecting the coin wasn't behaving according to normal physical laws. As the data continued pouring in from observatories around the world, the astronomical community found itself facing an uncomfortable truth. Either Atlas represented the most anomalous natural object ever discovered, breaking multiple established rules of physics and chemistry simultaneously, or their fundamental assumption that it must be natural was wrong. The consensus that had formed so confidently just weeks earlier was crumbling under the weight of accumulating evidence. Scientists who had spent their careers studying comets were finding themselves unable to explain what they were seeing using any known natural processes. Atlas wasn't behaving like a comet. It wasn't behaving like an asteroid. It wasn't behaving like anything in their experience of how objects should behave in space. And that realization forced them to confront a possibility that most had never seriously considered. What if everything they thought they knew about interstellar visitors was about to change forever? To understand just how unprecedented Atlas was becoming, you need to know about its predecessors. In the entire history of human astronomy, we had confirmed exactly 3 objects that originated outside our solar system. Think of them as the first explorers from an unknown continent, each one teaching us something different about the space between stars. The first was Oumuamua in 2017, a strange elongated object about 240 meters long and 40 meters wide, shaped like a cosmic cigar tumbling end over end through space. What made Oumuamua so puzzling was what it didn't do. It showed no signs of the outgassing that characterizes comets, no coma, no tail, yet it somehow accelerated slightly as it moved away from the sun. It was our first glimpse that interstellar visitors might not behave exactly as we expected. Then came Borisov in 2019, and this one was a relief to astronomers everywhere. It behaved like a textbook comet, developing a beautiful coma and tail as it approached the sun, showing all the right spectral signatures of sublimating ice, even fragmenting near perihelion in exactly the way comets are supposed to fragment. Borisov told us that our theories about comets were fundamentally correct. Interstellar space was populated by objects that followed familiar rules. But Atlas was something else entirely. The scale difference alone was staggering. If you imagine Oumuamua as a bicycle and Borisov as a car, then Atlas was like a cruise ship, With an estimated diameter exceeding 5 kilometers and a minimum mass of 33 billion tons, it outweighed its predecessors by 3 to 6 orders of magnitude. This wasn't just a bigger version of what we'd seen before. It was a completely different category of object. And this creates a fundamental problem with our understanding of how interstellar space should be populated. If objects the size of Atlas were naturally common, we should have detected millions of smaller objects first. It's like finding elephants in a forest before you've ever seen a single ant. The size distribution of debris ejected from planetary systems should follow predictable patterns, with far more small objects than large ones. Think about it this way. When planetary systems form and giant planets migrate inward, they scatter material of all sizes, but the smaller pieces are much more numerous and much easier to eject completely from the system. Finding a massive object like Atlas as only our third confirmed interstellar visitor is like opening a bag of mixed nuts and having the first 3 pieces you pull out be coconuts. The space between stars should be dominated by pebbles and boulders, not mountains. Yet here was Atlas, a monument-sized object traveling through interstellar space with no obvious explanation for how something so large could have survived the ejection process and the billions of years that followed. Atlas had been wandering through space for approximately 4.6 billion years, enough time for our entire solar system to complete one full orbit around the galactic center. During that incredible journey, it would have been constantly bombarded by cosmic radiation energetic enough to gradually erode any normal material. Occasional impacts from microscopic dust grains, hitting at relative velocities of dozens of kilometers per second, should have sandblasted its surface smooth and created clouds of debris. For any natural object to remain structurally intact through such an ordeal, it would need exceptional strength and cohesion, properties that seem incompatible with the loose aggregates of ice and dust that characterize typical comets. But the real mystery deepened when astronomers studied Atlas's light patterns in detail. The variations in brightness as it rotated didn't match what you'd expect from a simple rocky body tumbling through space. Instead, it showed brightness changes that seemed to follow their own mysterious rhythm, like a light that was pulsing according to some internal logic, rather than just reflecting sunlight from different angles. The early spectroscopic observations had shown only a reddish color, typical of dust-covered objects, with none of the characteristic gas emission lines that active comets display. It was like detecting smoke without fire, or smelling perfume without finding flowers. The normal signatures of comet activity were simply absent when they should have been obvious. When gas emissions were finally detected, they revealed that bizarre 87% carbon dioxide, 4% water composition that inverted every known rule about how comets should be made. In our solar system, even the most CO2-rich comets still contain far more water than carbon dioxide. Finding the reverse ratio was like discovering a glacier made primarily of dry ice with just a sprinkle of regular ice mixed in. The metallic composition was equally baffling. Spectroscopic analysis showed nickel abundances exceeding iron, completely contradicting the universal patterns seen in chondritic meteorites, asteroids, and every other rocky object in our solar system. This reversal of normal metal ratios was like finding a type of steel where the alloy was stronger than the base metal. Perhaps most disturbing was the discovery of that antisolar jet. Normal comets develop tails and jets that always point away from the sun because sublimating ice creates pressure that pushes material outward. But Atlas was somehow directing material toward the sun, as if it were actively drawing something from the surrounding space, rather than simply outgassing in response to solar heating. The rotational stability was another red flag. A period of exactly 15.5 hours suggested a solid, coherent body with the kind of structural integrity you'd expect from manufactured metal, not the loose collection of debris that should characterize an ancient comet. Objects that have wandered through space for billions of years should show signs of impact damage, irregular rotation from past collisions, or complete fragmentation from thermal stress. The orbital alignment was perhaps the most unsettling anomaly of all. Atlas's trajectory was aligned with our solar system's ecliptic plane to within just 5 degrees, like a car that somehow managed to follow the exact center line of a cosmic highway despite supposedly driving at random. The probability of this happening by chance was less than 0.2%, and the planetary encounter sequence was even more precisely calculated. Atlas was going to pass within specific distances of Venus, Mars, and Jupiter with the kind of geometric precision that seemed far too convenient for an object following pure gravitational physics. It was like watching a billiard ball that had been launched randomly, yet somehow managed to bank off exactly the right spots to tour the entire table. The subtle non-gravitational accelerations detected by precision astrometry suggested something was occasionally adjusting Atlas's course in tiny increments. Like a car that makes imperceptible steering corrections to stay in its lane, these adjustments were far too small and controlled to be explained by random outgassing from comet activity. Even the thermal properties defied explanation. As Atlas approached perihelion, it should have heated up and appeared redder due to thermal emission. Instead, it appeared bluer than the sun, violating basic principles of blackbody radiation that govern how hot objects emit light. But perhaps the most chilling discovery was the directional correlation with the famous WOW signal detected by SETI researchers in 1977. When astronomers traced Atlas's trajectory back to its point of origin, they found it aligned to within 9 degrees of that legendary 72-second radio burst that had tantalized scientists for decades. For a random interstellar trajectory, the probability of this alignment was only 0.6%. It was as if Atlas had been sent from the same region of space that had produced the most compelling potential evidence for artificial signals in the history of radio astronomy. Each individual anomaly might be dismissed as a rare but natural phenomenon. Unusual chemical compositions exist. Objects can survive long journeys through space. Orbital alignments do occasionally occur by chance, but when you start multiplying these independent probabilities together, you quickly reach numbers so small they become essentially impossible. It's like flipping a coin and having it land heads 20 times in a row. Technically within the realm of possibility, but so unlikely that any reasonable person would start suspecting the coin wasn't obeying normal physical laws. As data continued accumulating from observatories worldwide, the pattern became increasingly clear. Atlas wasn't just unusual. It was exhibiting a coordinated set of behaviors that seemed to follow some kind of internal logic, rather than the random physics of a natural object drifting through space. And that forced astronomers to confront a question they had never expected to face seriously. What if Atlas wasn't natural at all? But before we dive deeper into that unsettling possibility, you need to understand the cosmic context we're dealing with. Our solar system isn't an isolated island in space. It's more like a bubble floating in an ocean of interstellar material, constantly being crossed by visitors from the depths of space. Picture our solar system as it really is, extending roughly 100,000 astronomical units from the Sun to the heliopause, where the solar wind finally gives way to the interstellar medium. That's a sphere of space so vast that light takes nearly a day and a half to cross from one side to the other. And at any given moment, this enormous volume contains thousands of objects that originated elsewhere, Current estimates suggest that at least 10,000 objects the size of Oumuamua exist within Neptune's orbit right now, most of them too small or too distant for our telescopes to detect. They're like cosmic ghosts, drifting silently through our neighborhood on trajectories that will carry them back into the darkness between stars. With next-generation telescopes like the Vera Rubin Observatory coming online, we expect this to change dramatically. Instead of detecting one interstellar visitor per decade, we should start finding them every few months. The era of treating these objects as extraordinary rarities is about to end. Soon, studying interstellar visitors will become as routine as cataloging asteroids. Most of these objects travel at speeds between 20 and 60 kilometers per second relative to our Sun. Fast enough to cross our entire solar system in just a few years, but slow enough that we have a reasonable chance to study them if we detect them early. These velocities aren't random. They reflect the typical speeds of stars moving through our galactic neighborhood. The origin story of these wanderers is both violent and inevitable. When planetary systems form around young stars, massive planets don't stay where they originally condense. They migrate inward through the disk of gas and dust, their gravity scattering smaller objects like billiard balls flying off a table after a particularly violent break shot. Some material falls into the central star, some settles into stable orbits, but a significant fraction gets launched into interstellar space with enough velocity to escape the system permanently. The scale of this ejection process is staggering. For every object we detect crossing our solar system, millions more remain invisible, either because they're too small to reflect enough sunlight or because they pass through regions of space where our telescopes aren't looking. We're seeing just the tip of an enormous iceberg of interstellar material. Think about our own Kuiper Belt for perspective. This collection of icy objects beyond Neptune contains perhaps 1 trillion individual bodies. If our solar system is typical, gravitational perturbations should eject roughly 1 Kuiper Belt object into interstellar space every 10 million years or so. Multiply that by the 100 billion stars in our galaxy, and you get a mind-numbing population of wandering objects. Even with conservative estimates, there should be trillions of interstellar objects drifting through the space between stars right now. A vast diaspora of rocky and icy debris from billions of planetary systems that have evolved over the galaxy's 13 billion-year history. The journey times involved are almost incomprehensible. An object traveling at 30 kilometers per second would take approximately 30 million years to cross the distance between nearby stars. That's geological time from our perspective, but it's practically instantaneous on cosmic scales. Over the age of the galaxy, these objects have had time to mix thoroughly, creating a truly galactic population of wanderers. But here's the challenge with detecting them. Our current telescopes can only spot interstellar objects when they pass within about 5 astronomical units of the Sun, roughly Jupiter's distance. This creates an incredibly narrow detection window. Most visitors remain completely invisible until they're practically on top of us, and then they're gone again within months or years. This observational bias means we preferentially detect large, active objects while missing the vast population of smaller, inactive visitors that probably make up the majority of interstellar traffic. It's like trying to study wildlife by only counting the animals that walk directly past your front porch. You'll see some interesting specimens, but you'll miss most of the ecosystem. The orbital mechanics of these encounters follow strict rules. Objects with orbital eccentricity greater than 1.0 are on hyperbolic trajectories that will never bring them back. They follow open paths through space-time, like cosmic parables that intersect our solar system once and then extend to infinity. Unlike comets from our own Oort cloud, which return periodically, interstellar visitors are one-time events. The probability of any random interstellar object passing close to multiple planets is extraordinarily low. It's like throwing a dart blindfolded and hitting several specific targets in sequence. The gravitational cross-sections of planets are tiny compared to the vast spaces between them. For Atlas to line up encounters with Venus, Mars, and Jupiter with mathematical precision seems to defy reasonable odds. Even when planetary encounters do occur, they can only slightly modify an object's trajectory. The gravitational influence of our planets isn't strong enough to permanently capture something moving at interstellar velocities. These visitors are just passing through, temporarily perturbed, but ultimately continuing on their endless journeys through space. The window for detailed study is frustratingly brief. Most interstellar objects remain visible for only a few months to a few years. Barely enough time to organize comprehensive observational campaigns with multiple telescopes. By the time we've confirmed that an object is truly interstellar and not just a long-period comet, it's often already heading back toward the outer reaches of our solar system. Solar heating temporarily activates icy objects during their closest approach, creating the comas and tails that make detection easier but simultaneously complicate analysis of their original composition. It's like trying to study an ice sculpture while someone is melting it with a blowtorch. The very process that makes these objects visible also alters the properties we're trying to measure. The surfaces of these ancient wanderers bear the scars of their billion-year journeys. Cosmic radiation gradually alters surface chemistry, creating weathered crusts that can mask the original composition underneath. High-energy particles and occasional micro-impacts slowly sandblast exposed surfaces, potentially hiding the true nature of the material beneath. Some interstellar objects might even be influenced by the weak magnetic fields that permeate our galaxy. Objects with magnetic properties or electrical charges could experience subtle course corrections over millions of years, following slightly curved paths through space rather than perfectly straight lines. These effects would be nearly impossible to detect, but could accumulate over cosmic timescales. As objects approach our sun, they encounter the solar wind, a stream of charged particles flowing outward at hundreds of kilometers per second. This creates measurable radiation pressure on small objects, an effect that's negligible for massive rocky bodies, but could be significant for lightweight or unusually structured materials. Looking ahead, the future paths of our 3 confirmed interstellar visitors are already determined. Oumuamua has already passed Neptune's orbit and is racing toward the heliopause, never to return. Borisov is following close behind, nearly at the edge of our solar system, and Atlas will eventually follow the same route of permanent exile, disappearing into the interstellar darkness from which it came. Each of these objects represents a unique archaeological specimen, a sample of conditions and processes that occurred in alien stellar nurseries billions of years ago. They're like cosmic time capsules, carrying information about how planetary systems form and evolve in environments very different from our own. But Atlas was different from the others in ways that went far beyond simple size or composition. What made Atlas truly extraordinary wasn't just its anomalous properties, but how those properties seemed to work together in ways that suggested something more than random chance. In astronomy, we have a specific term for things that don't fit our established understanding. We call them anomalies. Think of an anomaly as finding a fish living in a tree, technically possible under some bizarre set of circumstances, but so improbable that it forces you to question whether your basic assumptions about how the world works are correct. When Avi Loeb, the Harvard astrophysicist who had already stirred controversy by suggesting Oumuamua might be artificial, first analyzed the Atlas data, he catalogued 8 distinct anomalies. But as more observations poured in from telescopes around the world, that list grew to 15 separate characteristics that defied conventional explanation. Each one, taken alone, might be dismissed as a rare but natural phenomenon. But when you start combining independent improbabilities, the mathematics becomes deeply unsettling. The first enigma was purely statistical. The probability of detecting an interstellar object over 20 kilometers in diameter within just 5 years of serious searching was calculated at roughly 0.001. To put that in perspective, it's like buying 4 lottery tickets and winning the jackpot on each one. Technically possible, but so unlikely that any reasonable person would start suspecting something unusual was happening. The second anomaly was that inverted chemical composition we discussed earlier. Having 87% carbon dioxide and only 4% water vapor reverses the typical ratios seen in every comet ever studied. It's like discovering a beach made primarily of seashells with just a sprinkle of sand mixed in. Such compositions aren't theoretically impossible, but they violate our understanding of how icy objects form in the cold outer regions of stellar systems. The third peculiarity involved metallic abundances that broke fundamental rules of cosmochemistry. Spectroscopic analysis showed nickel exceeding iron in Atlas's composition, contradicting patterns seen in every known type of rocky object in our solar system. In every natural environment where metals condense from stellar material, iron always dominates over nickel by substantial margins. This reversal was like finding wood where the bark was harder than the heartwood. The fourth anomaly appeared in the polarization measurements. Light reflected from Atlas showed polarization patterns that didn't match any known models for how electromagnetic radiation scatters off ice, dust, or rock. It was as if the surface materials were obeying their own unique optical laws, interacting with light in ways that our physics textbooks don't describe. But perhaps the most disturbing discovery was how rapidly Atlas had brightened as it approached the sun. The increase in luminosity was far more dramatic than sublimation physics should allow, like ice melting faster than heat could possibly penetrate the surface. Normal comet brightening follows predictable curves based on how solar radiation gradually warms subsurface materials. Atlas was brightening as if it had its own internal energy source. The thermal properties were equally impossible. As Atlas reached perihelion, it should have appeared redder due to thermal emission from its heated surface. Instead, it appeared bluer than the sun itself, violating basic principles of black-body radiation that govern how hot objects emit light. It was like watching ice that somehow became more transparent when you heated it. That antisolar jet remained one of the most physics-defying observations. Normal comets expel material away from the sun because sublimating ice creates pressure directed outward. But Atlas was somehow directing a focused stream of material toward the sun, behavior that would require either an external force pulling matter inward or some kind of active propulsion system working against natural physics. The orbital alignment probability was calculated at 0.2%. Atlas's trajectory was aligned with our solar system's ecliptic plane to within just 5 degrees. Like a cosmic vehicle that had somehow managed to follow the exact center line of an invisible highway through space. Random interstellar trajectories should show no preferred orientation relative to our planetary system. Even more unsettling were the planned planetary encounters. Atlas was going to pass close to Venus, Mars, and Jupiter with mathematical precision that seemed far too convenient for an object supposedly following pure gravitational physics. The probability of such a sequence occurring by chance was calculated at less than 0.05%. Like watching a randomly thrown ball that somehow managed to bounce off 3 specific targets in perfect sequence. The correlation with the famous "wow" signal sent chills through the SETI community. When astronomers traced Atlas's trajectory back to its point of origin, they found it aligned to within 9 degrees of that legendary 72-second radio burst detected in 1977. For a random direction in space, this alignment had only a 0.6% probability of occurring by chance. Perhaps most disturbing was the realization that Atlas had approached our solar system along a path that would make early detection nearly impossible. Coming from the direction of the galactic center, it had traveled through dense star fields, where distinguishing a moving object from the background would be extraordinarily difficult. If you wanted to approach our solar system without being noticed until the last moment, this would be exactly the route you'd choose. Advanced astrometric measurements revealed another impossibility. Atlas's rotation axis remained aligned with the Sun-Atlas direction throughout both its approach and departure phases. For this synchronization to occur naturally, the combined probability worked out to 0.00025, like flipping a coin and having it land on heads 16 times in a row. High-resolution imaging showed that the material jets remained collimated across hundreds of thousands of kilometers, maintaining focus with precision that seemed inconsistent with the chaotic sublimation of natural ices. Normal comet jets spread and diffuse rapidly due to thermal motion of gas molecules, but Atlas's outflows maintained their directional coherence far longer than physics should allow. The Jovian encounter parameters provided perhaps the most mathematically precise anomaly. Atlas's closest approach to Jupiter would occur at exactly 53.445 million kilometers, practically identical to Jupiter's Hill radius of 53,502 million kilometers. This is the boundary of Jupiter's gravitational sphere of influence, the perfect distance for releasing smaller objects that would become permanent Jovian satellites. The precision of this alignment defied reasonable odds for coincidence. Precision orbital tracking detected those subtle non-gravitational accelerations that suggested something was occasionally making small course corrections. These tiny velocity changes were far too controlled and purposeful to result from random outgassing. It was like watching a car that occasionally made imperceptible steering adjustments to stay perfectly centered in its lane. When you step back and look at the complete pattern, something even more unsettling emerges. These weren't just random anomalies scattered throughout Atlas's behavior. They formed a coherent sequence of characteristics that, taken together, resembled intelligent navigation, strategic masking, and precise positioning. The combination suggested purposeful design rather than natural coincidence. Individual anomalies might be explained away through rare but natural processes. Unusual chemical compositions exist. Objects can occasionally survive long journeys through space. Orbital alignments do sometimes occur by chance. But when 15 independent improbabilities occur simultaneously in the same object, the mathematics becomes overwhelming. It's like that coin-flipping analogy, but extended far beyond reasonable limits. When you flip a coin and it comes up heads 25 times in a row, you don't need to be a statistician to suspect something unusual is happening. The coin might be weighted, or someone might be controlling the outcome, but you can be fairly certain it's not behaving according to normal probability. The combined probability of all Atlas's anomalies occurring naturally approaches zero so closely that it becomes functionally impossible. We're talking about odds comparable to winning every lottery on Earth simultaneously while being struck by lightning and finding a perfect diamond in your backyard, all on the same day. This convergence of impossible coincidences forced astronomers to confront a possibility that most had never seriously considered. What if Atlas wasn't exhibiting anomalous natural behavior, but rather perfectly normal artificial behavior? What if the reason none of their models could explain Atlas was because they were trying to understand a manufactured object using theories designed for natural phenomena? The threshold of credibility for natural explanations was rapidly approaching zero, forcing serious consideration of alternatives that challenged everything astronomers thought they knew about interstellar visitors. And that realization opened a door to possibilities that would forever change humanity's understanding of its place in the cosmos. To truly grasp what Atlas might represent, you need to zoom out and consider the vast stage on which this drama is unfolding. Our Milky Way galaxy is approximately 13.6 billion years old, nearly as ancient as the universe itself. That's enough time for 360 generations of civilizations, each lasting 10 million years. Think about what that means. If intelligence arose regularly throughout galactic history, there could have been entire cycles of technological species that rose, flourished, and either transcended or disappeared long before our sun even began to form. The numbers are staggering when you consider the potential for life, with roughly 100 billion stars in our galaxy, and conservative estimates suggesting that 10% have planets in habitable zones around sun-like stars. We're looking at 10 billion potential cradles for life and intelligence. Even if only 1 in a million of those actually developed technological civilizations, we'd still be sharing the galaxy with thousands of other intelligent species. But here's what makes the timeline so important. Most stars in our galaxy formed billions of years before our sun. The thick disk region, where Atlas appears to have originated, contains some of the oldest stellar populations in the Milky Way. If technological civilizations arose around those ancient stars, they would have had a head start measured not in thousands or millions of years, but in billions. The technological gap between such civilizations and humanity would be comparable to the difference between modern humans and bacteria. This leads us directly to one of the most profound questions in science. If intelligence is common in the universe, and if civilizations have had billions of years to develop and expand throughout the galaxy, where are they? This is the famous Fermi paradox, and Atlas forces us to confront it in a completely new way. One possible answer comes from science fiction writer Liu Cixin's dark forest hypothesis. Perhaps advanced civilizations remain deliberately silent and hidden because the universe is full of predatory intelligences that eliminate any competition they detect. In this scenario, revealing your existence to other technological species is tantamount to suicide. Civilizations become like nocturnal predators, staying quiet and invisible to avoid attracting the attention of even more dangerous hunters. But there's another possibility that's almost more unsettling. Perhaps advanced civilizations are already here, quietly observing and studying younger species like ourselves. After all, interstellar travel isn't actually impossible with current physics. Our own Voyager probes, launched with 1970s technology, will eventually cross the entire galaxy in about 1 billion years. A civilization with even modest technological advantages could build vessels capable of much faster interstellar journeys. Imagine a civilization that had 1 billion-year head start on technological development. Their capabilities would be so far beyond ours that we might not even recognize their artifacts as artificial. We'd be like bacteria trying to understand a computer chip. The very concepts needed to comprehend their technology might be beyond our current cognitive capacity. And this brings us to Atlas. If advanced civilizations wanted to send exploration probes or even small habitats to investigate other star systems, objects the size of Atlas would make perfect sense, large enough to contain sophisticated instruments or even self-sustaining populations. yet small enough to make the journey without requiring impossibly vast amounts of energy. The masquerading strategy would be brilliant. Approaching through the galactic center region, using the dense stellar background as camouflage, would be exactly the kind of operational security an advanced intelligence might employ. If you wanted to observe a developing civilization without triggering a panic or contaminating their natural evolution, covert surveillance would be the logical approach. Atlas's trajectory allows close inspection of multiple planets in our solar system, which would be ideal for a reconnaissance mission studying a potentially habitable world. The mathematical precision of the planetary encounters suggests a carefully planned survey rather than random gravitational mechanics. Consider the timing of the journey. If Atlas originated in the galactic thick disk and traveled at its observed velocity of 60 kilometers per second, it would have been en route for approximately 4.6 billion years. That means this journey began when Earth was just forming, when our planet was still a molten ball of rock being constantly bombarded by asteroids and comets. But here's what's truly remarkable about that timeline. Artificial structures could potentially survive such an interstellar voyage if they were designed with the right materials and engineering principles. Unlike natural comets, which are loosely bound collections of ice and dust, a manufactured object could be built to withstand billions of years of cosmic radiation, micro-impacts, and thermal cycling. During that vast journey, whoever sent Atlas would have had ample opportunity to detect signs of life on Earth. Our planet's oxygen-rich atmosphere has been detectable from interstellar distances for at least 2 billion years, serving as a clear biosignature that would flag Earth as potentially interesting to any advanced civilization conducting systematic surveys of the galaxy. Human radio transmissions, on the other hand, have only been propagating through space for less than a century, creating a sphere of detectability that extends barely 200 light-years from Earth. A tiny bubble in galactic terms. So while an advanced civilization might have known about Earth's biosphere for billions of years, they would have only recently detected signs of technological intelligence here. The timing of Atlas's arrival seems almost perfectly calculated. It reached our solar system just as humanity developed the technological capability to detect and analyze interstellar visitors. Before the 21st century, Atlas could have passed through our neighborhood completely unnoticed, but it arrived precisely during the narrow historical window when we have automated survey telescopes scanning the skies and sophisticated instruments capable of detailed spectroscopic analysis. Even Atlas's approach velocity seems optimized for its mission. 60 kilometers per second is fast enough for efficient interstellar travel, but slow enough to allow precise gravitational maneuvering around multiple planets. It's exactly the speed you'd choose if you wanted to conduct a thorough survey of our solar system, rather than just flying through at maximum velocity. The approach angle is equally strategic. Coming from the southern celestial hemisphere, Atlas avoided the regions of space under most intensive astronomical surveillance. The majority of our major observatories and asteroid detection programs are located in the northern hemisphere, where they naturally focus more attention on the northern sky. The hyperbolic trajectory allows Atlas to execute what spaceflight engineers call an Obeth maneuver, using our sun's gravity to change direction and gain velocity with maximum energetic efficiency. This is exactly how we design interplanetary missions to minimize fuel requirements and maximize scientific return. Most intriguingly, Atlas's closest approach to Jupiter occurs at almost exactly Jupiter's Hill radius, the boundary of Jupiter's gravitational sphere of influence. This would be the perfect location to release smaller objects that would become permanent satellites of Jupiter. establishing a long-term presence in our solar system even after Atlas itself continues into interstellar space. If Atlas were indeed artificial, it would represent the first confirmed evidence that non-human intelligence is actively investigating our solar system. Not just that life exists elsewhere, but that it has achieved interstellar travel capabilities and is sufficiently interested in our little corner of the galaxy to send sophisticated reconnaissance missions across billions of years and trillions of kilometers. This possibility forces us to reconsider everything we think we know about our cosmic neighborhood. We might not be alone in the darkness between stars. We might be under observation by intelligences so advanced that their surveillance technology appears to us as nothing more than an unusual comet. The implications extend far beyond astronomy into philosophy, sociology, and the very core of human identity. If Atlas is artificial, then we are no longer the only explorers in our galaxy. We become the explored objects of study for minds that achieved technological mastery while our world was still cooling from its formation. And that realization would mark the beginning of an entirely new chapter in human history. As 2025 drew to a close and observations of Atlas continued pouring in from every major observatory on Earth and in space, the scientific community found itself approaching a moment of truth that no one had anticipated. All the data was converging toward a conclusion so disturbing that it challenged the very foundation of how we understand objects in space. Every observation, every measurement, every spectroscopic analysis pointed toward the same unsettling reality. Atlas was fundamentally defying our understanding of how natural objects should behave in the cosmos. The accumulation of evidence had reached a critical mass that could no longer be ignored or explained away through increasingly creative theoretical gymnastics. But here's the frustrating reality facing astronomers. They were like detectives trying to solve a crime with only blurry photographs taken from a great distance. Despite having some of the most sophisticated instruments ever built, they were bumping up against fundamental limitations in what current technology could definitively determine about an object millions of kilometers away. The crucial test was going to be detailed spectroscopic analysis of that impossible antisolar jet. If Atlas were a natural comet, the material streaming toward the sun should consist of typical cometary gases like carbon dioxide and water vapor, moving at velocities of hundreds of meters per second, as predicted by sublimation physics. But if Atlas were technological, that jet might represent some kind of propulsion or collection system operating at velocities measured in thousands of meters per second. The scientific community faced a stark dichotomy. Either Atlas represented the most anomalous natural object ever discovered, simultaneously breaking multiple established rules of astrophysics and chemistry, or it was the first confirmed example of extraterrestrial technology visiting our solar system. There seemed to be no middle ground left. The problem was that astronomers found themselves in the position of horse experts trying to identify an automobile. Their entire training and expertise was built around understanding natural objects, comets, asteroids, planets, stars. These were the phenomena that filled their textbooks and defined their careers. The possibility that they might be looking at manufactured technology had never been seriously considered in their education or professional experience. Avi Loeb had proposed a classification system to quantify how artificial an object might appear. A scale from 0 to 10, where 0 represented clearly natural interstellar debris and 10 represented unambiguously alien technology. Based on the accumulated evidence, Atlas was scoring somewhere between 4 and 6, firmly in the ambiguous zone where natural explanations became statistically implausible, but technological explanations remained speculative. This created what philosophers of science call a burden of proof problem. Instead of trying to prove that Atlas was artificial, perhaps scientists should be asking why they automatically assumed it must be natural, despite the mounting evidence of impossibly coordinated anomalies. The default assumption of natural origins might itself be the error that was preventing clear analysis. The instrumental limitations were becoming painfully obvious. Earth's telescopes had been designed to study conventional astronomical objects like stars, galaxies, and familiar solar system bodies. They weren't equipped for forensic analysis of potentially artificial objects that might be employing unknown materials, energy sources, or engineering principles. It was like trying to perform brain surgery with kitchen utensils. Time was running out. Atlas had already passed perihelion and was racing away from the sun, growing fainter with each passing day. The window for detailed observations was closing rapidly, and with it, humanity's chance to definitively characterize the most potentially significant object ever detected in our solar system. If Atlas were indeed technological, then it had executed a perfect solar gravitational assist maneuver, the same Oberth technique that human mission planners use to maximize velocity changes while minimizing energy expenditure. The mathematical precision suggested not just intelligence, but intelligence sophisticated enough to plan complex orbital mechanics across interstellar distances and billions of years. The orbital coincidences had moved beyond the realm of reasonable probability, simultaneous alignment with the ecliptic plane, precisely calculated planetary encounters, arrival from the direction of a historic radio signal, approach through the galactic center's camouflaging star field, rotation synchronized with solar direction. Closest approach to Jupiter at exactly the hill radius boundary. When you multiplied all these independent probabilities together, the chances of natural coincidence approached zero. Here's what was truly unsettling. Humanity could detect Atlas easily with current technology, but characterizing its true nature appeared to be beyond our current capabilities. We were in the frustrating position of being able to observe something potentially revolutionary while lacking the tools to prove what it actually was. Atlas was forcing astronomy to confront a possibility that had always lurked at the edges of scientific speculation. What if not everything we observe in the cosmos is natural? What if some objects in space were manufactured by intelligences using principles and materials beyond our current understanding? The entire framework of astronomical science might need to expand to include the possibility of artificial phenomena. If Atlas were technological, it would represent the first successful detection of extraterrestrial intelligence. But through a completely unexpected pathway, instead of radio signals from distant civilizations, we might have stumbled upon archaeology, physical artifacts left behind by explorers who had mastered interstellar travel long before humans even existed. But humanity had no established protocols for responding to such a discovery. No government agency, no international organization, no scientific institution had prepared for the possibility that we might detect alien technology passing through our solar system. The discovery was falling into a bureaucratic and intellectual void with no clear procedures for how to proceed. Proper analysis would require unprecedented interdisciplinary collaboration. Astrophysicists, aerospace engineers, materials scientists, and perhaps even experts in a field that didn't yet exist. Xenoarchaeology, the study of artifacts created by non-human intelligences. The scientific community was being forced to invent new methodologies in real time. The computational models told a stark story. Every simulation designed to reproduce Atlas's behavior using known natural processes failed catastrophically. the observed patterns of brightness, rotation, outgassing, and orbital mechanics simply could not be replicated using conventional comet physics. It was like trying to explain the flight of a jet aircraft using the mathematics of bird aerodynamics. A critical test was approaching in March 2026. If Atlas were to release smaller objects during its closest approach to Jupiter, positioned precisely at Jupiter's Hill radius, it would provide virtually irrefutable evidence of technological intent. Natural comets don't strategically deploy satellites at gravitationally stable positions around gas giants. What was happening with Atlas paralleled a historical precedent. Just as Oumuamua had forced astronomers to recognize that interstellar visitors actually exist after decades of theoretical predictions, Atlas might force acceptance that some of those visitors are artificial. Science was being compelled to expand its conceptual boundaries once again, at its core. Atlas confronted humanity with the most fundamental question possible. Are we alone in the universe? Or are we being studied by intelligences that achieved interstellar travel capabilities billions of years before our species even existed? The answer to that question was racing away from us at 60 kilometers per second, carrying its secrets toward the edge of our solar system and back into the darkness between stars. And with each passing day, the window to definitively answer that question was closing forever. But beyond the scientific implications, Atlas was forcing humanity to confront something far more profound than just another astronomical discovery. If this object were indeed artificial, it would fundamentally redefine our position in the cosmos. We would no longer be the galaxy's only explorers, boldly venturing into the unknown. Instead, we would be the explored. Subjects of study for intelligences so advanced that their reconnaissance missions had been crossing interstellar space since before our planet had even cooled from its formation. Think about what that means for human identity. A civilization capable of constructing Atlas would have mastered engineering challenges thousands of years beyond our current capabilities. They would have solved the problems of interstellar propulsion, materials science capable of withstanding billion-year journeys, and navigation systems precise enough to target specific planetary systems across galactic distances. Their technological mastery would dwarf our achievements the way our smartphones surpass stone tools. Yet the very fact that such technology might have visited our solar system suggests something remarkable about Earth itself. We must be interesting enough, rare enough, or valuable enough to justify the enormous expense of an interstellar investigation. In a galaxy with 100 billion stars and countless planets, something about our little corner of space has attracted attention across impossible distances. For all of human history, we've looked up at the stars and wondered if anyone was looking back. Every culture, every civilization has asked the same fundamental question: are we alone in the universe? Atlas suggests that not only might we not be alone, but that they have been aware of us far longer than we've been capable of wondering about them. Consider the timeline. If Atlas truly began its journey 4.6 billion years ago from the galactic thick disk, it was launched when Earth was still a molten ball of rock, constantly bombarded by asteroids and comets. At that time, our planet showed no signs of life, no oxygen in the atmosphere, no indication of the biological complexity that would eventually emerge. Yet something about this young world warranted investigation across billions of years and trillions of kilometers. The implications are staggering. This suggests not just casual observation, but systematic, long-term monitoring of planetary evolution, as if advanced civilizations routinely dispatch probes to young star systems to track their development over geological timescales, waiting to see which worlds might eventually develop life and intelligence. If Atlas is artificial, Its approach strategy reveals something profound about the intentions of its creators. The careful masking during approach, the route through the galactic center's dense star fields, the timing that avoided detection until we had developed the capability to study it, all suggest a civilization that prefers observation without interference. They seem to follow something like Star Trek's Prime Directive, a policy of non-interference with developing civilizations. This realization forces us to reconsider other anomalous astronomical events throughout history with fresh eyes. How many unusual comets, irregular asteroids, or unexplained phenomena might have been artificial objects that we simply lacked the knowledge or technology to recognize as manufactured? The historical record of astronomy might be peppered with unrecognized encounters with alien technology. Compared to a civilization with billions of years of development, humanity exists in a state of technological infancy. We're like children playing with sandcastles on a beach, while an ocean of cosmic possibility extends beyond our comprehension. Our entire history of technological development, from the first stone tools to spacecraft and computers, represents perhaps a few seconds in the lifespan of a galactic civilization. Yet here we are, potentially facing the most significant discovery in human history. Our generation might bear the responsibility for confirming the first direct evidence of extraterrestrial intelligence, not through radio signals or mathematical messages, but through the physical presence of technology created by minds that solved the challenges of interstellar travel eons before humans existed. This discovery could mark the transition of astronomy from a purely observational science to something more like archaeology, the systematic search for and study of artifacts created by non-human intelligences. We might need to fundamentally restructure how we approach the study of space, looking not just for natural phenomena, but for the signatures of design and purpose. How we respond to Atlas might serve as a test of humanity's maturity as a species. Are we approaching this potential discovery with scientific curiosity and measured analysis, or are we reacting with fear, denial, or aggression? Our response might determine whether we are considered ready for more direct contact, or whether we need more time to develop the wisdom necessary for cosmic citizenship. If Atlas is indeed an observer, then our reaction is itself being observed. Every decision we make about how to study this object, how to interpret the data, how to respond as a species, might influence future interactions with intelligences that have been watching our development for longer than we've existed. We're potentially being evaluated based on our scientific maturity and emotional stability. The confirmed existence of alien technology could force humanity to transcend the national, ethnic, and cultural divisions that have defined our history. When faced with the reality that we share the cosmos with superior intelligences, the differences between human cultures might seem suddenly trivial. We could be compelled to unite as a single planetary species rather than competing tribes. Knowledge that we're being observed by advanced civilizations might revolutionize human priorities. The resources we currently spend on warfare and conflict might be redirected towards scientific exploration and technological development. Knowing that we're part of a larger cosmic community could inspire us to accelerate our own development to become worthy participants in that community. This could explain the great silence that has puzzled SETI researchers for decades. If advanced civilizations prefer discrete observation to direct communication, then the absence of obvious radio signals makes perfect sense. They're studying us, not trying to talk to us, at least not yet. The timing of Atlas's arrival seems almost perfectly calculated. It reached our solar system precisely during the brief historical window when humanity developed the ability to detect and analyze interstellar objects. But before we've achieved sufficient technological maturity to pose any threat to advanced civilizations, we are old enough to recognize the significance of the discovery, but young enough to be safely observable. If confirmed, the existence of alien technology would represent the greatest shift in human consciousness since Copernicus demonstrated that Earth orbits the Sun rather than being the center of creation. Every assumption about our uniqueness, our importance, our place in the cosmic hierarchy would need fundamental revision. The decisions we make about Atlas will echo through centuries. How we study it, how we interpret the data, how we respond as a species will establish precedents for humanity's relationship with cosmic intelligence. Future generations will judge whether we approach this moment with wisdom or fear, with curiosity or aggression. Our reaction to Atlas might itself be part of an assessment, a test to determine whether humanity has developed the scientific maturity and emotional stability necessary for eventual contact with civilizations that have mastered technologies we can barely imagine. We're potentially being evaluated on our ability to handle the most profound discovery in human history. Atlas represents the possibility of a cosmic awakening, the moment when humanity finally realizes that the universe is populated by intelligences that have been aware of us far longer than we've been capable of wondering about them. But whether this awakening leads to a new era of cosmic consciousness or remains forever an intriguing mystery depends entirely on what happens next. And time is running out to make that determination. But as we step back from the emotional and philosophical implications, what has Atlas actually taught us about the limits of human knowledge? Perhaps the most humbling lesson is how primitive our ability to recognize and categorize cosmic objects truly remains. We're like botanists from the 18th century encountering an entirely new form of life that doesn't fit into any existing classification system. Our taxonomies work perfectly for familiar phenomena, but when confronted with something genuinely unprecedented, our categorical frameworks break down completely. Think about what this means for scientific confidence. For decades, astronomers have felt increasingly certain about their understanding of how objects behave in space. We can predict planetary orbits centuries in advance, model stellar evolution across billions of years, and explain the formation of galaxies using well-tested physics. But Atlas has revealed that this confidence may be premature when applied to phenomena we've never encountered before. The experience with Atlas has revealed a vast chasm between detection and understanding. Our technology can spot a moving object millions of kilometers away, track its motion with extraordinary precision, measure its brightness variations to fractions of a percent, and even analyze the chemical composition of its surface materials using spectroscopy. But when it comes to determining the fundamental nature of that object, whether it represents natural processes operating according to known laws or artificial construction following unknown principles, we find ourselves frustratingly limited. It's the difference between being able to see something clearly and being able to comprehend what you're actually looking at. Consider the parallel with early microscopy. When Antony van Leeuwenhoek first observed bacteria in the 17th century, he could see tiny moving objects clearly, but had no framework for understanding what they were. Were they the smallest possible animals, particles of matter in motion, something else entirely? It took centuries of additional research to develop the conceptual tools necessary to understand that he was observing an entirely new category of life. Atlas is forcing an evolution of the scientific method itself. For centuries, astronomy has been built on the foundational assumption that everything we observe in space is natural, Stars burn according to nuclear physics. Planets orbit according to gravitational mechanics. Galaxies evolve according to the interplay of dark matter and cosmic expansion. This assumption has been so fundamental that it's rarely even stated explicitly. It's simply the background presumption that underlies all astronomical investigation, the possibility that some objects might be artificial, created by intelligences with their own purposes and technologies, requires a fundamental expansion of our investigative methodology. We need new categories of analysis, new types of evidence, new ways of distinguishing between natural and designed phenomena. This isn't just adding more instruments to existing telescopes. It's developing entirely new ways of thinking about what we might encounter in space. True science demands the intellectual courage to admit ignorance rather than forcing inadequate explanations into familiar categories. When faced with phenomena that don't fit existing models, the human tendency is always to stretch those models until they somehow accommodate the new data, no matter how contrived or unlikely the explanations become. It's like trying to fit a square peg into a round hole by hammering harder, rather than acknowledging that you might need a different shaped hole. Atlas challenges us to acknowledge when our understanding is genuinely insufficient, and resist the powerful psychological urge to explain away mysteries rather than confronting them honestly. This kind of intellectual humility is extraordinarily difficult for experts who have spent decades mastering their fields, only to discover that their expertise may be inadequate for the questions they're now facing. The study of Atlas has demanded unprecedented interdisciplinary collaboration that breaks down traditional academic silos. Astronomers trained to study natural phenomena have found themselves consulting with aerospace engineers familiar with spacecraft design, materials scientists who understand how artificial structures degrade over cosmic timescales, computer scientists who model navigation algorithms, and even anthropologists who study how intelligence manifests itself in technology and tool use. These are fields that rarely intersect under normal circumstances. An astronomer studying comet sublimation has little reason to collaborate with an engineer designing interplanetary probes. But Atlas has forced expertise from completely different domains to merge in real time, creating new hybrid disciplines that didn't exist before this discovery. Here's a stark reality we've discovered about the current state of human technology. While our detection capabilities have advanced dramatically over the past few decades, our analytical tools remain woefully inadequate for the existential questions Atlas is forcing us to ask. We can spot interstellar visitors routinely now, but determining whether they're natural debris or artificial constructs requires instruments, methodologies, and conceptual frameworks that simply don't exist yet. We're trying to perform forensic analysis of potentially alien technology using tools designed to study rocks, ice, and gas. It's like attempting to understand a computer by analyzing it with techniques developed for studying minerals. You might learn about the silicon and metal components, but you'd completely miss the information processing that represents the device's actual purpose. Atlas demonstrates how scientific preconceptions can create enormous blind spots that prevent us from recognizing extraordinary possibilities. The automatic assumption that everything in space must be natural may have caused astronomers to misinterpret or dismiss evidence of artificial objects throughout recorded history. How many unusual comets, irregular asteroids, or anomalous phenomena might we have rationalized away because the alternative seemed too improbable to consider seriously? This bias toward natural explanations is understandable and usually appropriate. In science, you always try simpler explanations before more complex ones, and natural phenomena are generally simpler than artificial ones. But when dealing with potentially unprecedented discoveries, this bias can become a cognitive trap that prevents recognition of genuinely new categories of phenomena. The objects that don't fit our existing categories are precisely the ones most likely to revolutionize our understanding of reality. Anomalies aren't inconveniences to be explained away through increasingly creative theoretical gymnastics. They're opportunities to discover that the universe is far stranger, more complex, and more populated than our current theories suggest. Atlas belongs to that rare category of observations that forces science to expand its conceptual boundaries rather than simply filling in details within existing frameworks. Historical examples abound. Pulsars seemed so artificial when first discovered that astronomers briefly considered whether they might be signals from extraterrestrial civilizations. The extreme regularity of their radio pulses seemed too precise for any known natural phenomenon. Only after extensive investigation did we develop theories of neutron stars that could explain this apparently artificial precision through natural physics. Our experience with Atlas reveals an urgent need for entirely new protocols, new instruments, and new methodologies specifically designed to identify and study possible artificial objects in space. We've stumbled into the era of space archaeology completely unprepared. Using tools and techniques developed for conventional astronomy to investigate what might be the most significant discovery in human history. The instruments we need don't exist yet, but now we know exactly what gaps need to be filled. High-resolution spectrometers optimized for detecting manufactured materials rather than natural minerals. Imaging systems capable of revealing structural details that might indicate design rather than natural formation. Navigation analysis software that can distinguish between trajectories shaped by gravity alone versus those modified by propulsion or guidance systems. The Atlas discovery also demonstrates something remarkable about the speed and effectiveness of modern scientific collaboration. Within weeks of the initial detection, observatories on 6 continents were coordinating observations, sharing data in real time, and collaborating across national, institutional, and cultural boundaries as if those boundaries didn't exist. When faced with cosmic mysteries, humanity naturally transcends its political divisions. We've learned that our global scientific community possesses impressive capacity for rapid response when confronted with truly extraordinary phenomena. Data collection, analysis, and worldwide coordination that might normally require months or years of planning was accomplished in weeks. This demonstrates that when humanity encounters something genuinely unprecedented, we have the institutional infrastructure to respond quickly and effectively. But Atlas has also revealed dangerous limitations inherent in scientific specialization. Experts who have spent their entire careers studying the sublimation chemistry of comets may be fundamentally ill-equipped to recognize artificial technology, even when looking directly at it. The depth of knowledge that makes someone a world-class expert in one narrow field can simultaneously create blind spots that prevent them from recognizing phenomena that fall outside their domain of expertise. This creates a paradox. The more expert someone becomes in understanding natural phenomena, the less likely they may be to recognize artificial alternatives. It's like becoming so skilled at reading books that you lose the ability to recognize when you're looking at a computer screen displaying text rather than ink on paper. The experience with Atlas demands a new kind of balanced skepticism that walks the narrow line between gullibility and closed-mindedness. We need to be skeptical enough to demand rigorous evidence and avoid jumping to dramatic conclusions based on insufficient data, but not so skeptical that we reflexively reject possibilities that challenge our existing worldview simply because they seem improbable. This balance is extraordinarily difficult to achieve. Too little skepticism leads to premature conclusions based on wishful thinking. Too much skepticism leads to dismissing genuine discoveries because they don't fit comfortable preconceptions. Atlas forces us to maintain both intellectual rigor and openness to possibilities we never expected to encounter. Atlas reminds us how incredibly recently humanity developed the ability to detect interstellar visitors at all. In the 13.8 billion year history of the universe, we've only possessed this capability for a few decades. We're cosmic newcomers, barely past our technological infancy, attempting to understand phenomena that may involve intelligences with billions of years of development behind them. The humility this perspective demands is both profound and uncomfortable. It's like insects that have just developed eyes trying to understand architecture by examining buildings. They can detect the structures, measure their dimensions, even analyze their materials to some extent. But comprehending the purposes, design principles, and construction methods requires a level of understanding that may be fundamentally beyond their cognitive capabilities. Our response to Atlas required instant international coordination that transcended normal institutional boundaries, demonstrating that truly cosmic questions automatically make earthly divisions seem irrelevant. When faced with potential evidence of extraterrestrial intelligence, scientists didn't ask which country owned the discovery, which institution deserved credit, or how the information should be controlled. They asked how humanity as a species could best understand what we were seeing. This natural transcendence of boundaries when confronting cosmic questions suggests that contact with genuine extraterrestrial intelligence might force humanity to evolve beyond its current tribal divisions toward a more unified planetary perspective. The instrumental and methodological gaps revealed by Atlas are specific and addressable, but will require sustained effort and investment. We need space-based telescopes designed specifically for detailed characterization of potentially artificial objects, rather than just detecting them. We need spectroscopic techniques optimized for identifying manufactured materials, engineered structures, and technological signatures, rather than just natural minerals and organic compounds. We need new analytical frameworks that can systematically distinguish between natural phenomena and designed systems without defaulting to either explanation prematurely. These tools and methodologies don't exist yet, but the Atlas experience has shown us exactly what needs to be developed. The timing of Atlas's arrival continues to raise profound questions about coincidence versus intentional design. It reached our solar system precisely when we had developed the technological capability to detect and study interstellar objects. But before we had achieved sufficient technological maturity that we might represent a threat to advanced civilizations. This timing could be purely coincidental, but it could also suggest that our development is being monitored by intelligences that carefully choose when to reveal evidence of their presence. If the timing is intentional, it suggests a level of long-term planning and patient observation that spans geological timescales. It implies that our technological development is being tracked and that contact protocols exist for species that reach certain milestones of scientific capability. Regardless of Atlas's ultimate nature, its discovery has already fundamentally transformed cultural conversations about extraterrestrial life, humanity's cosmic significance, and our readiness for contact with non-human intelligence. The questions it raises about artificial objects in space, the possibility of ancient monitoring civilizations, and the adequacy of our current scientific methods are now part of mainstream scientific and popular discourse. The cultural impact of these ideas extends far beyond professional astronomy into philosophy, religion, and human self-understanding. Atlas represents only the third confirmed interstellar object in human history, but statistical models predict that dozens or hundreds more are constantly passing through our solar system at any given time. Most remain undetected because they're too small, too dark, or pass through regions of space we're not monitoring closely. We need to be prepared for the next visitor with better instruments, clearer protocols, and a much deeper understanding of how to distinguish between natural phenomena and potentially artificial constructs. The discovery represents a fundamental transformation of astronomy, from passive observation of distant objects to active investigation of phenomena that might contain intelligence, purpose, and design. We're evolving from studying what the cosmos is to studying who might be in it. This shift from physics to archaeology, from natural philosophy to the search for mind and intention, marks a paradigmatic evolution in how we approach our relationship with the universe. This transformation will accelerate regardless of what we ultimately conclude about Atlas itself. The questions it has forced us to ask, the methodologies it has required us to develop, and the possibilities it has compelled us to consider seriously have permanently expanded the scope of astronomical investigation. And that expansion is only the beginning of a much larger transformation in humanity's understanding of its place in a cosmos that may be far more populated, more intentional, and more aware of our existence than we ever dared imagine. The story of Atlas may be ending, but the larger story it has initiated is just beginning. Atlas marks the dawn of a new era in human consciousness. A period where we must seriously consider that not everything we observe in the cosmos follows purely natural laws. This represents a revolutionary expansion of perspective that will ripple through science, philosophy, and human culture for generations to come. We are witnessing the birth of a fundamentally different relationship with the universe. One where the possibility of encountering intelligence beyond Earth has moved from science fiction to legitimate scientific consideration. The mystery of Atlas will likely persist, regardless of what conclusions future investigations might reach. Even if we never definitively determine whether it was natural or artificial, it has already transformed our understanding of how little we actually know about visitors from the depths of interstellar space. The questions it has forced us to ask will outlive any specific answers we might discover about this particular object. Think about the children growing up right now, the generation that will come of age knowing about Atlas and the possibilities it represents. They will develop a natural familiarity with concepts of space archaeology and the search for alien artifacts that previous generations never imagined. For them, the idea that some objects in space might be technological rather than natural will seem obvious rather than revolutionary. They will be the first humans to mature with the expectation that the cosmos might be populated by intelligence. The technological legacy of Atlas may prove as significant as its scientific impact. The urgent need to study objects like this will drive development of new telescopes specifically designed for artifact detection. Advanced spectrographs capable of identifying manufactured materials, and entirely new analytical techniques for distinguishing between natural and artificial phenomena. These innovations will benefit all of astronomy, even if they were originally motivated by the search for extraterrestrial technology. Atlas has created a bridge between humanity's ancient fascination with the stars and the tangible possibility that we are not alone. Every culture in human history has looked up at the night sky and wondered about the lights they saw there. Atlas connects that ancestral curiosity with the concrete prospect that some of those lights might be looking back. It transforms wonder into investigation, mythology into potential reality. Our response to Atlas is establishing precedents that will guide humanity's approach to future discoveries of possible extraterrestrial intelligence. The scientific rigor we apply, the international cooperation we demonstrate, the balance we maintain between skepticism and openness, all of these responses are creating templates for how our species handles encounters with phenomena that challenge our understanding of our place in the cosmos. Atlas is forcing an expansion of human identity itself. We are evolving from thinking of ourselves merely as inhabitants of Earth to recognizing that we might be participants in a vast galactic community. This shift in cosmic perspective will influence everything from our scientific priorities to our philosophical frameworks to our sense of responsibility as a potentially observed species. The discovery demonstrates something remarkable about the democratization of space exploration. Atlas was detected not by a government agency or military installation, but by an automated survey telescope operated by an international collaboration. This shows that cosmic exploration is no longer the exclusive privilege of superpowers, but has become a globally accessible endeavor that transcends national boundaries and political divisions. Understanding Atlas completely may require decades of patient investigation, teaching us that the most profound cosmic questions demand generational patience rather than immediate gratification. The greatest discoveries often reveal themselves slowly, requiring sustained attention and gradual accumulation of evidence. Atlas reminds us that some mysteries are worth pursuing even when quick answers aren't possible. In a galaxy containing 100 billion stars and 13.6 billion years of evolutionary history, perhaps objects like Atlas are actually normal, and our limited experience on a single world around a single star is the exception. We may need to completely recalibrate our sense of what constitutes ordinary versus extraordinary in cosmic terms. What seems impossible to us might be routine for civilizations with billions of years of development. Atlas rewards the intellectual courage required to question fundamental assumptions about reality. Perhaps the greatest discovery isn't determining whether this specific object is artificial, but recognizing how little we actually know about our cosmic neighborhood. The willingness to admit ignorance and remain open to possibilities beyond current understanding represents a crucial form of scientific maturity. Regardless of its ultimate nature, Atlas represents one link in an unbroken chain of human exploration that began when our ancestors first looked up at the stars and wondered what they were seeing. This chain of discovery extends from ancient astronomical observations through Galileo's telescope to modern space missions, and will continue with future generations who will possess instruments and knowledge we can barely imagine. Atlas teaches us a profound lesson about scale and significance. We can be simultaneously insignificant in cosmic terms, yet apparently interesting enough to warrant investigation across interstellar distances. This paradox suggests that while individual humans and even our entire civilization may be tiny on galactic scales, the phenomenon of life and intelligence itself may be rare and valuable enough to justify the enormous effort of interstellar reconnaissance. The coming decades will bring more objects like Atlas, transforming astronomy from passive cataloging of distant stars and galaxies to active investigation of possible intelligence distributed throughout the cosmos. We are transitioning from asking what the universe contains to asking who might be in it. This represents a fundamental evolution in the goals and methods of astronomical science. Even if Atlas ultimately proves to be natural, it has already accomplished something irreversible. It has forced humanity to seriously confront the possibility that extraterrestrial technology might be visiting our solar system. This mental expansion cannot be undone. Once you've genuinely considered that the universe might be populated by intelligence, you can never return to the assumption that it must be empty. Atlas represents a cosmic invitation for humanity to mature as a spacefaring civilization and potentially join a galactic community of explorers that may have been active for billions of years. Whether we accept this invitation depends on how we develop scientifically, technologically, and perhaps most importantly, psychologically over the coming centuries. The story of Atlas will be told to future generations as an example of how scientific curiosity and open-minded investigation can lead to discoveries that fundamentally transform our understanding of reality. It demonstrates that the most important breakthroughs often come not from confirming what we expect to find, but from remaining alert to possibilities we never anticipated. Atlas reminds us that as the only known species capable of contemplating the universe and questioning our place within it, we bear a special responsibility to investigate cosmic mysteries with both wisdom and courage. Our unique position as conscious observers of the cosmos comes with an obligation to pursue truth wherever it leads, even when that pursuit challenges our most basic assumptions about reality. Perhaps most importantly, Atlas has renewed hope that the universe is far more interesting, populated, and wonderful than our limited experience on a single planet had suggested. It opens the possibility that reality contains levels of complexity, intelligence, and purpose that we are only beginning to glimpse. This renewed sense of cosmic possibility represents one of the most valuable gifts any discovery can provide. Atlas is not the end of a story, but the beginning of a new era where humanity finally starts to comprehend that we may not be alone in the cosmos, and that this realization is merely the first step in a much larger adventure that will define our species' development for millennia to come. As Atlas slowly disappears into the depths of space, carrying its secrets beyond the reach of our telescopes, it leaves behind something precious. The certainty that the cosmos still holds mysteries capable of transforming our understanding of reality. We may never know with absolute certainty whether Atlas was a natural visitor or an artificial one. But that uncertainty is itself a gift. It forces us to remain humble, curious, and open to possibilities that transcend our current experience and knowledge. In a galaxy containing trillions of stars and billions of years of evolutionary history, it would be extraordinary arrogance to assume that we are the only intelligence looking up at the stars and asking, "Is anyone else out there?" Atlas teaches us that the answer to that question may be much closer than we ever imagined, not in the distant depths of space, but passing silently through our own cosmic backyard, waiting for us to develop sufficient wisdom to recognize visitors when they arrive. The adventure has only just begun. If you're still awake, it's because the content was really good. So take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.